Hi everybody. So this lecture is on section 13.2 on the post hoc test on one-way analysis of variance. So this is basically what you would want to do after you perform the ANOVA test in 13.1. And so there's really only one objective in this section, which is to perform what's known as the Tukey test, named after John Tukey. Um, so um, when the results from a one-way ANOVA lead us to conclude that at least one population mean is different from the others, we can make additional comparisons between the means to determine which mean or means differ significantly. And the procedure for making these comparisons are called multiple comparison methods. So let's look at the one and only objective in this section, which is to perform the Tukey test, or Tukey's test. So the computation of the test statistic for Tukey's test for comparing pairs of means follows the same logic as the as the test for comparing two means from independent samples. However, the standard error that is used is given by the standard deviation squared over 2 times 1 over the sample size 1 plus 1 over the sample of size 2, and then taking the square root. And again, in this case, S squared is the mean square estimate. So, let's look at a further information here. So the test statistic for Tukey's test, given when you're comparing whether two sample means are equal versus whether they're different, again, is given by this. Again, where S squared is the mean square estimate of sigma squared, and N1 is the sample of size or population 1, and N2 is the sample size of population 2. The critical value for Tukey's test using a family-wise error rate alpha is given by this, where V is the degrees of freedom due to error, and in other words N minus K, and K is the total number of means being compared. So let's say we want to find the critical value from the studentized range distribution with V equals 13 degrees of freedom, K equals 4 degrees of freedom with a family-wise error of alpha equals 0.01. We'll find the critical value from the studentized range distribution with V equals 64 degrees of freedom and K equals 6 degrees of freedom with a family-wise error rate of 0.05. So in this case, the solution is given by this. Now, as far as Tukey's test is performed, after rejecting the null hypothesis, the following steps can be used to compare pairs of means for significant differences, provided that, again, there are K simple random samples from K populations. The K samples are independent of each other. The populations are normally distributed, and the populations have the same variance. And I should mention too that we can, for the previous result here, we can look in table 9 for that value. So for Tukey's test, the first step would be to arrange the sample means in descending order. Again, this procedure is outlined on the purple box in the bottom of page 639 as well. And then compute the pairwise difference between each one of your samples, where, again, the first sample has to always be greater than the mean for the second sample, and then compute the test statistic for each pairwise difference. So you'd want this value on top to be positive. And then determine the critical value, again, from table 9 in the back of your book. And if the calculated statistic is different from the value that we look up in the table, we will reject the null hypothesis that the two pairs are equal and conclude that the means are significantly different. And then you'll have to compare all pairwise differences to identify which means differ. So again, you'll have to sort of do this in pairs. So to just give you an example here, let's say that so we've determined that there is sufficient evidence to conclude that at least one of the means are different, and the mean square error from the ANOVA is found to be 28.7. The sample means are given by these three numbers, and we'll use Tukey's test to determine which pairwise mean are significantly different, using alpha in this case to be 0.05. So the means in ascending order are given by the following, so then compute the pairwise differences. Again, these should all be positive numbers over here. And then plugging into the formula, we'll see that for the sample 1 and 2 we get 6.22. For sample 2 and 3 we get 4.442. And for sample 1 and 3 we get 1.79. So we'll find the critical value again in the table 9. So for alpha equals 0.05, for 24 and k is equal to 3, we get 3.532, and then we just have to compare that to the calculated values that we got. So since 6.22 and 4.422 are greater than the critical value, but 1.79 is less than 3.532, we reject the fact that these two are equal and these two are equal, but not that mu1 and mu2 are equal. And so the conclusion of Tukey's test then are that mu1 and mu3 are equal. That's basically what this means with the bar underneath it, but that mu2 is not equal to mu1 or mu3. So hopefully that'll give you guys sort of an idea of what to do in this section. I should maybe mention that there are a couple things you do have to worry about Tukey's test. If you look on page 642, sometimes the results of Tukey's test can be ambiguous, and so you might have something where, say for example, 3 means are equal, and then another mean is equal to one of the means, but it doesn't necessarily mean it's equal to the other ones. So, so this basically means that at least one type 2 error has been committed by Tukey's test, and so it can also happen that the one-way analysis of variance rejects the fact that the means are equal, but Tukey's test does not detect any pairwise differences. And this occurs because a one-way ANOVA is more powerful than Tukey's test. And again, the solution in this case would be to increase the sample size. I'm not planning on giving you anything where that would happen on the exam, but just something to be aware of. Like I said, I don't think I'm going to have you actually do Tukey's test on the exam. I think I'll just have you do an analysis of variance there. But anyway, so so the next section we'll look at then is section 13.3 on complete randomized block design. And so in this case that we're going to be talking about things where you might have multiple variables and a single factor is manipulated and fixed at different levels. So we'll look at that in the next section, and this is basically used for controlling experimental error. Again, if you guys need help or have questions about anything, just let me know.